Hey guys, Assalamualaikum. Welcome back to another virtual lecture. In this video, we will learn another non-parametric method called the Goodness of Fit Test. Now, if you remembered in the last video, we learned about hypothesis test for proportions, right? And in that test, we used the normal distribution. However, for the Goodness of Fit test, we will use another distribution called the chi-square distribution. Now, let's take a look at how the chi-square distribution looks like. As you can see, the chi-square distribution looks very similar to the F distribution in that it is positively skewed. The value of chi-square is non-negative. See, the smallest value is 0, and it extends up to positive infinity. And just like the other distributions, there's also a family of chi-square distributions that is based on degrees of freedom. When the degrees of freedom change, a new distribution is created. And as the degrees of freedom increases, the distribution approaches the normal distribution. So here's how the table looks like. In order to read the chi-square table, all you need are two things. One is the alpha, or the level of significance. Okay, and since it's positively skewed, technically there's only one tail, right? Okay, so here are the alphas. And the other important thing you need to know is the degrees of freedom. Okay, so to calculate the degrees of freedom is a bit different than the way to calculate the degrees of freedom for an F distribution and a T distribution. I'll show you how to do that when we go to the examples. So, what is the goodness of fit test all about? Now, this test is commonly used when we want to compare an observed frequency to an expected one. Okay, so now let's take a look at the two types of frequencies, yeah? You know what frequencies are, right? When there's a tally or a count of something. Okay, now there are two types of frequencies here. One is the one that we expect, or expected frequencies, and the other one is which we observed. Okay, so the way we symbolize or denote the expected frequency is FE. Okay, and the way we denote observed frequency is FO. All right, so now understand that bit first. We've got two types of frequencies, the one that we expect it to happen and the one that we observed, or the actual frequencies that happened. Now, if there was a good fit, what that means is whatever we expected would be exactly equals to whatever we observed, right? It's a good fit. But if it is not a good fit, then what we expected is not the same as the observed. For example, if I expected 100 students to be in my class, if I go into the lecture theater and I actually see 100 of you sitting there, then there's a good fit between my expectations and the reality. Okay? However, if I expected 100 students, but I only see 75 students in the lecture hall, therefore there is not a good fit between what I expect and what I observed. So now let's take a look at how to conduct the goodness of fit test. Okay? Now, as always, the same 6 steps applies. However, there are differences in the way we write the hypothesis in step 1, as well as how to calculate the test statistic in step 3. Let's take a look at how to write the null and alternate hypothesis for a goodness of fit test. Now, the understanding of these concepts is very important for you to know how to write those two hypotheses, okay? So now, for step 1, remember we want to write down the hypothesis. Remember, the null hypothesis always assumes equals. You know, there is no difference, okay? So remember here we've got two frequencies, right? Expected frequency and observed frequency. So the null hypothesis would be to assume that there is no difference between our expected frequency and the observed frequency, okay? So there is no difference between our observed frequencies and expected frequency. Okay, what about our alternate hypothesis? It will be the opposite. There is a difference. Okay, so there is a difference between our observed and expected frequencies. Okay, so what I'm showing you here is basically the general way to write the hypothesis for a goodness of fit test. However, as we will see later on when we do the examples, it is not that clear-cut, especially when it comes to interpreting the conclusion and the decision of our test. Now, step 2, as always, is to determine what our level of significance is, okay, so what is alpha? Now here's another difference, how to calculate our test statistic. As mentioned to you before, for goodness of fit test, we will not be using the Z distribution, nor would we be using the T or the F distribution. Rather, we will be using a new distribution called the chi-square distribution, okay? So, how to calculate this test statistic? It's this way, okay? The observed frequency minus the expected frequency. Square it over the expected frequency, and we would want to sum all of this because we will have more than just one observation, okay? Right, so I'm going to show you how to do this as we look at the examples later. So remember, what's FO? It's observed frequency. What's FE? It's expected frequency. Now, as you've seen from the table before, there is degrees of freedom, right? When we're using the chi-square distribution. So how can we find the degrees of freedom? The degrees of freedom is simply k minus 1, where k is the number of categories. Okay, moving on, step 4 is basically to determine what our critical value is. Okay, remember, chi-square distribution is positively skewed, so technically or effectively we'll only have one tail. So this would be our alpha, and this is where we will reject the null hypothesis. Here is the acceptance area where we will do not reject the null hypothesis. Here would be our critical value, and because it's chi-square distribution, our critical value will also be chi-square distribution. Okay, so how to look at it from the table? Remember, there are two things you need to look at, right? One is the alpha, or the level of significance, and another one is the degrees of freedom, which is k minus 1. Okay, now we will compare what we calculated from the test statistic in step 3, and we will see whether it falls in the acceptance or the rejection area. Then we will make the decision. Oh yeah, of course, don't forget to write down your rejection rule, yeah? Reject the null if the chi-square test statistic is greater than the critical value, which is this one. Okay, remember, this one is the test statistic, and here is the critical value. And then you proceed with steps 5 and 6. 5 is to make the decision whether to reject or do not reject, and 6 is to make the interpretation or conclusion. Now, before we go on into the examples, allow me to highlight that when it comes to goodness of fit test, right, there are actually two types, okay? One is when we have the case of equal expected frequencies, okay? Equal expected frequencies. And the other case is when we have an unequal expected frequency. Now, in other case, what we need to do is to find the expected frequencies first. Once we find the values of all of our expected frequencies, we will use these values to calculate the test statistic. Let's take a look at this example. It is for an equal expected frequencies case. A department store, A, has 4 competitors, B, C, D, and E. Store A hires a consultant to determine if the percentage of shoppers who prefer each of the 5 stores is the same or not. A survey of 1,100 randomly selected shoppers is conducted, and the results about which one of the stores shoppers prefer are listed below. Using the goodness of fit test at the 5% significance level, is there evidence to conclude that the proportions are really the same? All right, so the first thing we need to do is to determine what is our expected frequency and what is our observed frequency. Now for that, I've written down the table here. Right, so this is basically the table that was given to us in the question. Okay, so we need to identify first what is our expected frequency, FE, and what is our observed frequency. So first things first, what are all these numbers? Okay, so this is the number that's given to us by the question. So normally whatever is given to us, that is the observed frequencies. Okay, so let's put it down here. This is our FO. This is our observed frequencies. Right, so what is FE? Okay, FE here, now if you recall the question, it states that, okay, let me just zoom in a bit. Okay, because we want to determine if the percentage of shoppers who prefer each of the 5 stores is the same. So this is basically the clue that tells us that the expected frequencies are equals. Okay, so now let's take a look at this table again. All right, So if the expected frequencies are equal for each of these 5 stores, how much would it be? That's right, 20%. 20%, 20%, 20%, 20%, and 20%. Why? Because if we add all of these percentages, we will get 100%. Okay, this is basically the percentage of the expected frequencies. What you really want to know is the number of shoppers. Okay, the number of shoppers that we expect. Now it's been given to us, right? The total number of random shoppers selected was 1,100, right? So the total number of observed shoppers would be exactly equal to the total number of expected shoppers. It will be the same, okay? But the individual values may be different, but the total will be the same, okay? So now how can we calculate the total number of shoppers for each of the stores? Very simple. We just take 20% multiply with 1,100, which is 220. So 220 for store A, 220 for store B, 220 for store C, and the rest. If you add all of this up, you'll get 1,100. And if you added the observed or the actual number of shoppers who like each of these stores, you'll also get 1,100. Okay, so this is basically our first step, which is to calculate the expected frequencies. And in this case, our expected frequencies are equals to each other, all right? Now, at this point, we can either continue to calculate the test statistic, or we can proceed with the step 1, step 2, etc. first, okay? So let's write it down. Let's see here, what is our first step? Or step 1, we want to write down the hypothesis, right? So the hypothesis, remember what we mentioned in theory is FO equals to FE. Okay, so that is basically the null hypothesis. But usually for the goodness of fit test, we don't usually write it as FO equals to FE. Okay, that would be too simplistic. So how do we write it here is we have to understand the context of the question. So in our story here, we know that there are 5 departmental stores, right? So store A basically wants to know if the percentage of shoppers who prefer their own store as well as the competitors are the same or not. So we can actually say, for instance, the null hypothesis is maybe you can say the customers prefer each of the 5 stores equally. Okay, customers prefer each of the 5 stores equally. Okay, so in other words, okay, this is just a fancy way of saying that our observed frequencies is actually equals to our expected frequency. Now, you don't really need to write this part. The reason why I'm writing this down is to tell you that this is what it means, okay? So there is no difference between what we expect and what we observed, okay? Because we're saying that the customers prefer each of these 5 stores equally. Alternatively, we're saying that, well, the customers do not prefer each of the stores equally, right? Customers do not prefer each of the stores equally. Each of the 5 stores equally. In other words, what this means is whatever is observed is not equals to whatever we expect. Okay? Now, step 2 is very simple. We just want to write down what our alpha is. So it's given in the question. Alpha is 5%. Okay, so here's the list of all of my observed frequencies, and here's the list of our expected frequencies, which are equally proportioned. Okay, see, the total here should be the same. Okay, so how do we calculate our test statistic? Let's look at it one by one. This is store A. So it's FO minus FE, and then square it over FE. So FO is 262 minus 220. Okay, so this one, it gives us 42. Okay, so this 42, we square it, which will give us 1764. Then we divide it with FE, 262 again. So this basically gives us 8.018. Okay, so do the rest for all of the stores. So this here, 14.618, would be our test statistic. Okay, now let's move on to step number 4. Okay, we would want to know what is the critical value. Okay, this is our area of rejection. Okay, reject the null, and the alpha is 5%. Okay, so this is the area of acceptance. So it's do not reject. Do not reject the null hypothesis. So let's take a look at our table to see what is the critical value. Okay, so this is our chi-square table. Okay, remember our alpha is 5%, right? So it's here. And our degrees of freedom, in this case, we have 5. Remember, the way to calculate the degrees of freedom for a chi-square is k minus 1. K is the number of categories. So from our question, there are 5 stores, so k is 5. 5 minus 1 is 4, okay? And 5% is here, so 4 and 5%. This one will give us our critical value, 9.488. So let's just write it down here. 9.488. Okay, right, so let's write down our rejection rule. We will reject the null if our test statistic is what? Greater than 9.488. So now let's move on to steps 5 and 6. Let's compare. This is our test statistic, guys. 14.618. So where does it fall? In the acceptance or rejection area? It's here. It's really big, so it's somewhere in the rejection area. So what do we need to do? We reject the null. Okay, since the test statistic lies in the, oops, you can see that, rejection area. Okay, we reject the null hypothesis. Okay, highlight that. To conclude, let's go back and look at the hypothesis in step 1. Okay, so we're saying reject, right? So reject the null, so we take the alternate. Okay, we take this one. So what do we say? We conclude that the customers do not prefer each of the 5 stores equally. Okay, so we can continue with our conclusion. We conclude that the customers do not prefer each of the 5 stores equally. Do not prefer. Okay, let's take a look at the second example of our goodness of fit test, but this time it is for an unequal expected frequencies case. Okay, so over the years, the demand for admissions in a university showed 30% for bachelor's degree, 25% for diploma courses, 20% for master's degree, 10% for PhD degree, and 15% for professional courses. A researcher, curious to know whether the demand pattern has changed, took a random sample of 400 newly admitted students, and the following result was obtained. Test whether the pattern of demand for the above programs have changed at the 5% level of significance. Be sure to show all of the 6-step hypothesis testing procedure. Let's begin by writing our hypothesis, step 1, okay? Now remember, the null is always there's no difference between FO and FE. Right? So in other words, when we talk about the question just now, has the demand pattern for admissions changed or not? Okay, so if it's if FO is equals to FE, we're saying that the demand for all of those, you know, courses, PhD, master's courses, degree, has not changed. Okay, so the demand pattern for admissions has not changed. Okay, because when we say it doesn't change, what it means is whatever we expect is exactly equals to whatever is observed. Okay, so it has not changed. However, if whatever we observed is different from what we expected, then of course it has changed, right? So the demand, okay, the demand pattern for admission has changed. Right. So you know that the null hypothesis basically means FO equals to FE, and the alternate hypothesis is basically FO not equals to FE. Then we can proceed with step 2, which is our level of significance. Given to us, it's 5%. Yeah, 5%. Moving on to step 3, which is to calculate our test statistic. Now, before we can do this, we need to determine what are our observed frequencies and expected frequencies. All right, so what I'm going to do here is basically just to, just draw back whatever information that the question gives us. Okay, so this is a list of all of the programs. Okay, what are the programs? We have a bachelor program, then we have a diploma. And then we have a master's program, PhD, and professional. Okay, so the way the question was given to us was horizontal. Okay, so here I've just changed it to become vertical so that we can see the calculation a bit easier, a bit more clear, right? So number of students, okay, all of this again, these are all given in the question, yeah? 125, 95 diploma students, 82 master students, 42 PhD students, and 56. Now, if you were to add all of them, okay, since the question gave us 400 students, were taken at random, so all of this is 400. Okay, so what are these? Okay, this is basically the observed frequency. Okay, remember guys, usually whatever is given to us is the one observed or actually happened. Okay, so this is our FO. So what we need to find now is the FE. Okay, so that is why there are two types of FE or expected frequencies. Our expected frequencies are either equals to each other, just like our previous example, or in this example, our expected frequencies are not equals to each other, okay, because they have given us the percentages. What's the percentages? Percentages of expected frequencies are given. So for bachelors, it's said that 30% of those being emitted goes to bachelor. Then we've got 25% of diploma students, 20% of master student, 10% of PhD students, and 15%. Okay, so how can we get the FE or the expected number of students? Very simple, because we know that the total for the FE should be the same, right? Okay, should be the same with the observed. So what we need to do is we just take the percentages that's given to us, we multiply with the total. So 30% of 400, it's 120. Okay, so now since we have both the observed frequencies and the expected frequencies, what we need to do is, because this is step 3, right? So what we want to do is we want to calculate our test statistic, which is chi-square. Okay, what's the formula? FO minus FE, and then the difference we square it, divide by expected frequency, and everything we add them all up. Okay, so instead of just writing down the working here, we can just show a working using the table, so it become a lot more clear. So FO 125 minus FE 120. Okay, so it's basically 5. Then we square the 5. Okay, it becomes 25 over FE 120. So what we'll have is 0.208. Okay, so maybe I should write this FO minus FE. We square it over FE. Okay, so do the rest for each and every one of the programs. Now moving on to step number 4. Okay, we want to know whether to reject or not reject this, so we need to compare it against the critical value. Okay, so here we have the chi-square distribution. Here's our rejection area. Alpha was 5% just now, right? So this is the area where we will reject the null. Here is the acceptance area where we will do not reject the null hypothesis. Okay, now let's take a look at the chi-square distribution table to know what is our critical value. Okay, so here, here's our chi-square distribution table. Now our alpha is 5%. Okay, our categories 1, 2, 3, 4, 5, 5. So there are 5 programs. Therefore, our degrees of freedom is 5 minus 1, k minus 1, which is 4, and here's 5%. So again, here our critical value is 9.488. So let's put it down here, 9.488. Okay, so let's write down our rejection area. Let's write down our rejection rule. Reject the null hypothesis if our test statistic is what? Yes, greater than 9.488. Okay, so now guys, let's okay, now for step 5 and 6, running out of space, but I didn't want to change to another page so that you don't miss out anything here. Okay, so now let's compare our test statistic calculated in step 3 with our rejection area in step 4. So where is this? 0.875 is definitely much smaller than 9.48, right? So this is somewhere where? Here. Right? Okay, so the test statistic lies in the acceptance area. It's here. So what do we say? Okay, since the test statistic lies in the acceptance area, what do? We do not reject the null. Okay, we do not reject the null hypothesis. So we look back at step 1, okay, where we wrote our hypothesis. So we've decided to not reject, right? So if we don't reject it, we will take the null hypothesis. So what do we conclude? We conclude that the demand pattern for admissions has not changed. Conclude that the demand pattern has not changed for admission. Has not changed. Okay, so we can underline our main points. There you go.